Fusion energy. The future of clean energy, or just a distant dream? For decades, it's been seen as the ultimate solution, a power source so vast it could reshape how we fuel our planet. One leader in this revolution is Tokamak Energy. With over a decade of innovation, they're not just dreaming about fusion, they're building it. Recently, alongside my co-founder Ben, we had the opportunity to explore Tokamak Energy's groundbreaking work firsthand. Game-changing for the clean energy space, which we've all been waiting for. But how close are we to seeing fusion light up the grid? Let's take a closer look. Well, Warwick, thanks so much for having us here at Tokamak Energy. It's amazing to see the facilities.
Yep.
Do you want to give us a bit of context as to why we're standing behind this big concrete wall?
Sure. Well, welcome, and thanks for coming to Tokamak Energy. And behind me, where we're going to go next, is ST40. That's a spherical tokamak and a 40 centimeter major radius for the technically savvy. And it's our R&D fusion machine that we've achieved amazing results on. And this is about 60 centimeters of concrete here that forms a shield all the way around the device, and that stops neutrons from getting out and harming people on the other side of the shield. So it's a really, really important bioshield for the safety of our employees while we're operating. This business was founded as a spin out from the UK Atomic Energy Authority.
Yeah.
We're actually in our 15th year now, but the results have really accumulated for Tokamak Energy in the last few years. In 2022, this machine achieved an incredible result, pushing plasma ion temperatures over 100 million degrees Celsius.
Wow.
So that's like 7-8 times the temperature of the core of the sun achieved in that device.
Wow.
So at that point in time, we were the hottest place in the solar system. And that is our business. We are developing fusion, technology, and designs of these tokamak machines for the future.
Clean, limitless, and potentially world-changing. But what does it really mean? To answer that, we had the chance to speak with Michael Ginsberg, president at Tokamak, to break down the science and the stakes behind fusion.
We know fusion works. You know, it's the stars, it's our sun. It's a huge challenge. It's probably one of the most challenging engineering and physics problems, that we faced. We've made real advancements in fusion energy in just the last, 20 years, leveraging all the research and science that has been done over, 80 years.
So if we think about the ST40, can you break down some of the key components that go into that?
Yeah, so ST40 is essentially what's called a spherical tokamak. So we take that traditional donut shape and then we squish it a bit, so make it more of a cored apple. That is the basis of our design, and we call that a low aspect ratio. What it is comprised of is, mainly a lot of magnets. We use copper in ST40 as a conductor, but in the future we're going to use high temperature superconductors because that is going to allow us to get to a much more energy efficient high field tokamak. There's all sorts of other elements that go into ST40, structural alloys, plasma facing components, breeder blankets. I would touch on the breeder blankets because that's important. Fusion is going to be a self-sufficient device in the future. What we take is relatively abundant materials, isotopes of hydrogen. You've got deuterium and tritium. And then we take neutrons that come out of the reaction. And with lithium, we produce more tritium. So that goes back into the fuel input into the device.
Fusion energy is no longer just an idea. It's becoming a reality. Around the world, companies and researchers are racing to unlock its potential. So where does Tokamak Energy fit into this evolving landscape? Fusion energy is one of the most exciting spaces within climate right now. Can you talk us through a little bit more about where Tokamak as a business sits within fusion?
Yeah, I mean, fusion is an exciting place. I kind of characterize it as it previously being the preserve of big government labs all around the world. And then in the last 15 or so years, we've seen this Cambrian explosion of fusion companies. The reason I joined this company is, essentially what we're doing is as hard as it gets. You've got to build, in my view, build on pedigree, build on heritage, There's over 60, 70 years of research in tokamaks. We've just decided that a spherical version of that device is the most efficient and lowest cost version, and that's why we're pursuing it. We're in the US program, which is developing a fusion pilot plant within 10 years. But we also can take our technology and know-how into other public-private partnerships. We believe that we can bring real value into the UK's program, STEP, that's the spherical tokamak for energy production. But also around the world, there are exciting programs emerging where we're playing a role as a design partner.
I like to say that we're perhaps the most credible path to fusion. With Tokamak Energy as the central designer, there are some really neat and unique concepts that are essentially being developed. These concepts have been around for quite some time. The 1950s onwards. Things like stellarators, things like mirror magnet devices. I think that the tokamaks have been the most thoroughly researched. And the game changers now are that we now are starting to realize that subsystem technologies like HTS magnets that are required to make them net energy output devices. But there's still a long road map forward for some of these other technologies that are now getting more funding. And it's exciting, but we shouldn't underestimate the challenges in front of us.
What would you say the biggest challenge is?
Well, certainly it's the HTS magnets in magnetically confined devices. I think on the inertial side, it's the precision engineering of the pellets, that are required, and then reducing the energy consumption of the lasers. But I would say the reason that a lot of these new concepts are gaining traction is because of AI. If you look at something like a stellarator, it's an interesting geometry. You've got all sorts of twists and turns, and it's really hard to confine the plasma in those types of devices. And so what you need is an AI algorithm that can predict where that plasma is going to go. That was something we couldn't do before, the advancements in computing that we currently have achieved.
So when you look at energy, you have a mix, you have a portfolio, and renewables take a slice of that, and we need them to because they're a source of clean energy. But the world needs baseload power, and it also needs high-grade industrial heat. Neither of those things are really suited to renewables. So they will always occupy maybe 30% of a country's portfolio mix, and the rest of that is pretty much burning fossil fuel.
Okay.
So that's the big slice we're going after with fusion for the future. So you can imagine a world where you have abundant, clean, safe energy provided by fusion, that the source of your fuel is essentially seawater and naturally occurring lithium. That's what you need. And you have got the world's next energy source. That's why companies are working so hard and labs are working so hard to create an industrialized version of this. But it is definitely the most valuable technology of this century, which is why it's such an immense prize to pursue.
Overcoming the challenges of fusion energy is only part of the journey. Turning groundbreaking research into a commercially viable energy source requires more than just innovation. It demands sustainable investment, global collaboration, and a clear path to scale. So, how does Tokamak Energy plan to make fusion a reality for the whole world?
You need a machine that produces a surplus of energy, obviously. You need more out than you're putting in. And that is often known in fusion as Q, a Q greater than 1. And that's been achieved at a fusion level around the world. But you need to achieve Q greater than 1, 3 or 4 at a whole system level. And that needs us to take machines like this into the next generation and scale them up. But then we need to think about how we industrialize these machines so they are around the world in their thousands and they're operating reliably. For us, that means we need very, very novel control systems, and that's where machine learning and AI can really play a role to control the plasma in the device. Then we need a thing called a breeder blanket, which goes around the outside of the vessel, and its job is to convert lithium into tritium, because then you have a closed loop fuel cycle. And you have big programs, including government programs around the world, that are seeking to perfect that technology. And another area we're focused on is how you protect surfaces within the device and things like your magnets. And that leads us to very novel shielding materials. So shielding materials to protect key components against neutron damage. Those really are the things we're going for to give us a pilot plant and then the plants that will be producing energy around the world thereafter.
I think it's fair to say that there is still a long way to go in terms of what's required from a capital standpoint to really commercialize not just Tokamak, but just fusion energy in general. How much capital do you think is needed across fusion energy to really get to commercialization? And when do you think that would be?
That's a great question. I think it's better than asking when's it going to happen, because my answer to that is usually, well, it's a function of the capital required. To build a pilot plant, which will essentially, prove out net energy output in a magnetically confined device, you were talking about several billions of dollars, right? Maybe a few. We're going to need several of those, and we're going to need to iterate on them. So, I think we're talking about, tens of billions of dollars to get to a first-of-a-kind situation. Once you're at a first-of-a-kind plant, you can start to drive down those with those economies of scale on the materials costs, and so that will get you to commercially competitive fusion.
Okay, there's just so much happening at Tokamak Energy. As you look into 2025, what are you most excited about?
I've been so excited in this past year just by how much we've been able to do as a team. The sort of cherry on top really has been this announcement of this brand new program, and I think we're gonna shut down the device, get the new materials in, integrate lithium, and we're gonna start to see some remarkable results in the next couple of years. But over the next year, I'm really excited about further developing, our U.S. presence, bringing some of the technologies that we've developed here into the U.S., both, new customers perhaps for our magnets, but also building out, our value proposition as a company in the U.S. and potentially, realizing both, other devices like an intermediate device on the way to a pilot plants with some of our partners, as well as, finding a site for a pilot plant. And then developing, partnerships to realize that.
Amazing. Well, Michael, thank you for hosting me and my team. It's been great to learn more about Tokamak Energy and also see the ST40 in real life.
Thank you. It's been a pleasure.
Our time at Tokamak Energy has been an eye-opening journey into the world of fusion energy, a technology with incredible potential to transform how we power this planet. We've explored the groundbreaking work happening here, met the passionate team driving innovation, and uncovered the challenges and opportunities ahead. To delve deeper into the future of fusion and what it will take to bring this to life, check out our full conversation with Michael Ginsberg, where he shares more insights on commercialization, global collaboration, and the path forward at Tokamak Energy. Today has shown us that fusion energy is closer than ever to becoming a reality, and the future of clean energy feels brighter than before.